Hi everyone, Mr. Lee here. In this video, we're going to go over electric potential. Let's begin. So in order to understand electric potential, I have to tell you all the different ways that we can call electric potential. Okay? So these are the synonyms, and these are the different ways in the problems that you might see. First off, it is difference. You might see it written as electric difference. You might see it as potential difference. You might see it as voltage. You might even see it as voltage difference. Okay? Now, these are the different ways that you can see electric potential be written. The equation for electric potential is capital V, for voltage, okay, capital V for voltage is equal to KQ over R. Now, sometimes you might just hear me say potential instead of voltage, but just so you know, they are synonyms and they are one and the same. Now, it is important to also have a little red flag here. What electric potential is not energy. I'll repeat. Electric potential is not electric potential energy. The two are not the same. You know what? In fact, I'm not even going to type that in there because I don't want you to see it and you'd be like, oh, okay, it must be synonyms. But just so you know, electric potential and electric potential energy are not the same. And we will cover electric potential energy in a later unit. But just so you know, one more time, electric potential energy is not the same as electric potential. Okay, so let's dive into this equation a little bit. Okay, first off, the units for electric potential is capital V for volts, and volts are joules per coulomb. Now, volts, it's named after a guy, Alessandro Volta, and so we use volts a lot, right? We hear about a 9-volt battery or a 12-volt battery, but volts are a unit, and sometimes with just units it doesn't really help us understand it. And so what I like to do is I like to always think about volts as joules per coulomb. Okay, and in fact, whenever you say something in volts, immediately in your mind you should think about joules per coulomb because it has a very significant meaning. Joules, of course, is the units for energy. Okay, and coulomb is a unit for charge. Now, if you remember, before I was saying electric potential is not electric potential energy. Okay, so the units for electric potential energy would simply be joules, but the units for electric potential is joules per coulomb. Once again, I need to emphasize they are not the same. All right. Now, to really understand electric potential, I'm going to go through different models. I'm going to go through different analogies, and this is one of those units where the more you sketch it out, the more you draw it out, the easier it is to understand. So the first thing I'm going to do is I'm going to do a quick little analogy of what is volts. What are volts? So a way that we can think about it is volts. Okay, we can think about it as height. Okay, or potential. We can think about potential as in it's like a height. All right, and this will really help us understand what it means when we're talking about electric potential. It's like the height, and of course, this is under the big umbrella of what we have here, as in the gravitational field, right? So, what this means, I'm going to do the gravitational field first. Is if we have the Earth. So let's say here we have the Earth. Hello, Earth. Okay, and we have, let's say, heights above the Earth. So let's say this is, 100 meters. Here above that we have 200 meters, and I'm not going to draw all the way. Here we have 300 meters, and here we have 400 meters, and so on, right? And, now we're all up in space. Okay, so in this analogy, Earth has above the Earth, we have a height. Okay, and within the Earth, right, the Earth, because it has a mass, I'm going to remind us here, the Earth has this thing called a gravitational field. And if you remember, the formula for gravitational field is Gm over R squared, right? And we drew the gravitational field like so, right? We drew the gravitational field like so. So what this means is if we have an object at a certain height, the gravitational field will accelerate that object towards the Earth. And of course, vice versa, Newton's third law. Now, this is important to know because I am here telling you that volts is a lot like height. Okay? So the further away that we go from the Earth, the height increases. But there's a flip side to it. Even though the height increases, the effects of the gravitational field, it'll get weaker and weaker. And the same is true also for when we think about the electrical side. So let's replace it. Let's think about V is equal to KQ over R. Remember, that's like our height. So instead, let's say we have a positive charge. Okay, a positive charge, and this positive charge has a positive field all around it. Right? Now, in the Earth scenario, this positive charge will be like the Earth. All right, so I'm just going to draw a couple more field lines. So if you remember from the Earth, I drew the height as these dotted lines. So I'm going to do the same, but for this charge. I'm going to have these dotted lines, and we're going to represent that as our potential lines. All right, I'll do that also. Let's do that in, let's do that in red. So around the charge, I have these dotted lines. All right, around the charge, I have these dotted lines. And these are my voltage lines. Okay, and oftentimes you'll hear me call these voltage lines my equipotential lines. Now, let's break this down. Lines are just lines. Potential is, potential. We can also think about that as voltage or volts, right? And equi means equal. So what this means is all along those lines, we have equal voltage. So let's go back to the Earth analogy. All right, so here in my Earth analogy, if I choose two different points, let's say I choose point A, oops, that's pretty big, point A right here, right? And I fly across the sky until I'm right here, and we can call that point B. All right, so we go from A to B. Now, if I were to ask you, did my height change? Let's say I'm in an airplane, right? Or I'm like Superman and I'm flying from point A to point B. And if I were to ask you, did my height change? The answer would be no. My height did not change. And that's because I was traveling along the same height. Now, if we use that same idea, but for potential, the same holds true. So let's say that along the first ring, we can call that first ring, let's say this is 100 volts. Okay. So if I were to look at two different spots, let's say I was looking at this first spot right here, okay, that location X, and let's say I were to go over here to this location, let's call this one Y, right? So we have location X and we have location Y. Because X and Y are along the same equipotential line, they will have the same voltage. It's as if I did not go up in height or down in height. I have the same voltage. Now, if I were to go from X to, let's say, up here, which is Z, I will have a change in voltage. And that is because it is a different equipotential line. Okay? So the equipotential lines, it tells us the same voltage. So all along, we have the same voltage. Now, before we go even further, I want to build this analogy of our Earth, of the terrain, and link it to the charges. So what I'm going to do is I'm going to draw for us two different scenarios. Okay, we're going to call this the mountain and the valley. Okay, so let's say we have a mountain. So this is the Earth, by the way. All right, let's say we have a mountain. And we have a valley. All right. And let's say this middle part, we can call this, I'm gonna draw my dotted line. We can call that like sea level, but we'll just call it height of 0 meters. Okay. Now, if we were to continue this analogy, right, of equipotential and height, we know that for this mountain, okay, if we walk up the mountain, so let's say this is us, if we walk up the mountain, we have a increase in height. If we go down the mountain, we have a decrease in height. Okay? And this is above what we call height 0. Now, for over here, we can go down into the valley. Okay, so that will be a increase in negative height, or we can go up out of the valley, and this will be a decrease So we're going towards the positive, right? We're going, we have a decrease in a negative height. So those are two different ways of thinking about it. Now let's flip this on its side, and instead of thinking about the Earth, let's think of this as electricity, right? Or electrical charges. And so the mountain is what we can consider to be a positive charge. Okay, and this valley here, well, that would be our negative charge. Our negative charge. And the change in the height will be the change in the voltage. All right. So if we go up towards the peak, we will be going towards a positive charge, and that will be a increase in positive voltage. Okay. But if we were to go down into the valley, we'll be getting closer to the negative charge, and that'll be just like a increase in negative voltage. So this is like a side profile model. I'm going to draw again what I just drew here, but in terms of like a flat scale. So here we have a positive charge, and here we have a negative charge. Okay. Now, I'm going to draw the field lines in a little bit, but what I want to do is I want to describe going up the mountain and going down the valley in this way. So let's say we start off here, right in the middle, okay, right where the height is 0, right where the voltage is 0. All right, so here we have a voltage of 0. If I am going towards, right, if I go towards the positive charge, this is as if I'm going up the mountain. In fact, I will write that there. I'm going up the mountain. Okay, I'm going towards the higher voltage. Now, if I go from here to here, I'm going down into the valley. Okay, I'm getting closer and closer and closer to this bottom pit. Now, here's something that you need to remember. Remember, positives and negatives just denote the type of charge that is being observed here. So don't think that if you have a bigger negative charge that things are getting smaller, right? That's just because we are getting more and more negative. We're not becoming smaller. We're getting more and more negative, right? So once again, if I go towards a positive charge, I have an increase in positive voltage. If I go towards the negative charge, I have a decrease in negative voltage. All right. So what about the other side? Now I'm going to do this in blue. Let's say I'm here on the mountain. If I go down the mountain, I'm headed towards this 0 line, right? And that is my 0 voltage. So my positive voltage will decrease. I'll show that here. So let's say I start off here and I go towards this 0 line. So here I have a decrease in positive voltage. All right, and let's say for here, I'm on this side of the valley, and I'm going up and out of the valley towards my 0 voltage. That's as if I am here. I am really close to the bottom of the valley, or I'm really close to that negative charge, and I am headed towards the 0 volts. So once again, what that means is that I have a decrease in negative voltage. I'm getting more and more positive. All right. Now let's go over how to draw the potential lines. All right. So the rule of the potential lines is very simple. We can say that the potential lines are always perpendicular to the field lines. And as a little note, field lines, okay, point away from positive, okay, and it points towards the negative. All right. Now this is important because when we are drawing the potential lines, we have to actually connect these two ideas together. Meaning that if the field lines are pointing away from the positive source, the further away you are from the source, the smaller the potential is. Okay, versus for like a negative source, right? The further away you are from the the negative charge, the the more zero potential you have. All right. So if I were to draw a couple of things, let's do the mountain scenario above. Right. So let's do the mountain scenario above. Actually, before we do that, let's do individual charges first. So here we have a positive charge. We have field lines there. I'm going to start off with 4, and then we can increase from there. Right. I'm just going to choose a point midway. Right. I'm going to do this in a different color. So let's do this red. Yeah. So right there, right, that line is perpendicular to my field line. And let's just say at this point we have 20 volts. Right. So right here, which is about midway, okay, I'm going to draw a line perpendicular, and we can say that's 20 volts. Same over here, midway, 20 volts, and right here, midway, 20 volts. Okay, so the important idea here is that it's all perpendicular. Now, if we were to draw more field lines, so I'm going to draw another one here, draw another one here, draw another one here, draw another one here. Okay, we can continue this. So about midway, we have 20 volts. About midway, we have 20 volts. About midway, we have 20 volts. And about midway, we have 20 volts. Okay. Now we can continue this for more and more field lines. We can do this for an infinite amount of field lines, and we can also draw the perpendicular equipotential lines. And what we end up getting is a region where all along these dotted lines we have the same potential. Okay. And if let's say we get closer to the charge, right? We'll do this in green or a different color. Let's say here, once again, perpendicular, because we're closer to the positive charge. Let's call this 100 volts, right? And here is 100 volts, here's 100 volts, here's 100 volts, here's 100 volts, 100 volts, 100 volts, 100 volts. So we can see that all along this inner green ring will be 100 volts. And we can do this again. We can get even further away. Now let's think about it. Okay, let's think about our mountain analogy. Now this is what I want you to do. If you're getting the hang of this, or if you're just getting used to this, I would always draw a mountain there, like in order to like really understand what's going on. So right now we have this positive charge. We drew the 100 volt, right? So this is the 100 volt height. Oops, one more. There we go. We drew the 20 volt height. Okay, the 20 volt height, and to wrap it up, we're going to draw, let's call this 5. Okay, all the way down here. This is a height of 5 volts. All right. So if we take a look at this, we can see that if the charge is all the way here, the 5 volts is the furthest away. And so I'm going to draw my 5 volt equipotential the furthest away from the the 100, the 20. Okay, so that blue ring will be my 5 volt. All right, and that's how we would draw for a positive charge. What about negative one? Well, the negative one is just the same. To start off, I'm going to draw my value there to know that down here it's negative. All right, so remember, the closer we are to the negative, and up here we have 0 volts. Okay, the closer we are to the negative, the more negative the voltage is. So before we actually sketch it out, I'm going to draw it over here. The first one, we can say this one is, let's say this is negative 50 volts. And the next one up here, we can say, remember, we're approaching 0. So a number that's approaching 0 that is not 50, we can say this is negative 30 volts. And really close up there to the top, we can say this is negative, 2 volts. All right, and so our diagram will reflect this. Okay, so I'm going to draw my negative charge here. I'm going to draw my field lines correctly, points towards the charge, points towards the charge, points towards the charge. And now I'm going to draw my equipotential lines. And remember, it has to be perpendicular, or just make it look like so that it is perpendicular. Okay, so really close to the negative will be negative 50. So I'm going to do that in green. So this will be my negative 50 volts. Further away will be my negative 30. So here will be my negative 30. Right, and even further away in blue, I have my negative 2 volts. Negative 2 volts, like so. All right, so this is what it looks like for individual charges. I'm going to wrap up this video with this dipole here. Dipole simply means that there are two charges that are opposite like so. And so let's do a positive and a negative. Okay, I'm going to zoom on in here. All right, field lines go away from the positive into the negative, away from the positive into the negative, away from the positive into the negative. Okay, and let's do one up here, away from the positive into the negative, away from the positive into the negative. And of course we have the ones that are on the outside fringes, like so. All right. Okay, so let's say these have the two of the same. We have two of the same charge values, so we can say right in the middle will be the 0 volts. Okay, so in terms of our analogy over here, the 0 volts is this horizontal, this dotted line here, where it's height 0. Okay, so that will be, it's going to do that in a thicker black. We can say right here, perpendicular to the line, that's 0. Perpendicular to the line, 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 0. So that's all my 0 volts. All right, now let's go up the mountain. So we just started off here at the 0 volts, but we're going up the mountain. Let's choose, we'll do this in red, we'll choose this height right here. Okay, and we will say this is 5 volts. All right, now if I were to draw my 5 volts, remember we're getting closer to the positive charge. So right here, that's going to be my 5 volt. And here, I need to draw my equipotential line that has to be perpendicular to the line. And you see here the line is sort of curving. So I want to reflect that. Okay, I want my equipotential at sort of an angle, and same here, I want this to be sort of at an angle, and right here, the field line is bending even more, so I want to really reflect that. So these are all my 5 volt lines, right? Okay, and let's go up the mountain even more. Let's say right here, that point, we'll make that 50 volts. Okay, so we're getting closer to the positive charge. All right, so here it'll be my positive charge, or my positive 50 volts here. Here will be my positive 50 volts here, and here will be my positive 50 volts there, right? And then we can create this ring-like effect. Now here's what's cool. Okay, if you look over here, I showed you that from the 0 going up the mountain, that's 5 volts. But notice on the other side, we also have 5 volts right here. Okay, so that's to the left of the charge. And the same will hold true over here. So what that means is, if I were to continue this around, okay, if I were to continue this around, like so, that means everything around there will be 5 volts. And the same is true for my 50 volts, right? If I were to just continue this equipotential around, that'll be my 50 volts. Of course, this is a sketch. It's actually slightly more exaggerated out, but our classwork will reflect that. All right, now let's go from the 0 volts and let's go towards the bottom of the valley. All right, we'll do this in, I guess, in green. Let's choose here. So this height over here, let's call that -7 volts. Okay. And so we can say here is -7 volts, -7 volts, -7 volts. Okay, going around, so we get this beautiful, beautiful concentric ring, and we can call that the -7 volts. And you know what? We're going to go deep into the valley there, and we will call this. Oh, let's use orange. Yeah, well, we're like really close. So down there, we can call that, I don't know, -75 volts. Right, so this is going to be really close to the negative charge. So we will say that this orange ring right there, that is your -75 volts. Okay. Now these are just the voltage points that we've chosen. You can actually find the voltage using the equation up here, V equals KQ over R, where Q is the charge that you're looking at. So for example, here we have a positive charge and the distance away, R. At that point, it'll tell you the voltage. And the cool thing is that voltage, it is a Voltage, it is a scalar, so the direction, it does not matter. So that actually helps us out when we're trying to find the voltage at different points. So let's take a look at a quick little example. Let's say we have two charges. We'll just do a quick problem here. Let's say we have a positive charge here, and let's say we have here a negative charge. I'll do this in red so that we can see it. We have a positive charge here, and we have a negative charge there. All right. So let's say the question is asking, what is the voltage at a certain point? And let's say that certain point, if we were to extend this x-axis, is right there, right? What is the voltage at this point? All right. Now, all we have to do is, because the equation is just V equals KQ over R. The only thing that you have to really think about is, well, two things. The important thing is how far away your charge is from that point, and of course the charge itself. Right. So for example, here, let's say this is a positive Q. I'm gonna make it simple for us. Let's say it's 2 coulombs, and this Q here is negative 5 coulombs. Okay, when we put into our equation, we would say that at point X, so V at point X will be K2 over, let's say from here to here, we'll call that R positive, whatever that distance is, plus K, here we have a negative 5, right, over, and then from here to there will be, this will be R negative plus R negative, right? And we can just add them all up and we can find the voltage at that point, right? So that's it. Let's just do a quick little recap of voltage. Think about voltage as it is, using an analogy. It's kind of like height. And I want us to keep on using that idea, because with voltage, we will get into electric potential energy. Voltage, also known as electric potential, goes by many different names, but as long as you do not see the word energy, know that you are dealing with voltage. The equation is very straightforward. A couple of rules when drawing electric potential, and we will be drawing electric potential for like FRQs and stuff. The electric potential is always perpendicular to the field lines. Okay, and these electric potential lines are also called as equipotential lines. And remember, equipotential just simply means all along that line we have the same voltage. Okay, you can either go towards a positive voltage source, or you can go towards a negative voltage source. But the important thing here is that if you're going towards something that is positive, your voltage will increase in magnitude, and vice versa. If you're going towards a negative voltage source, our magnitude will increase. So for example, negative 5 going towards a voltage source, we can make that negative 5 increase up to negative 500. Even though it's a small number, quote unquote, we're just looking at the magnitude. Okay. And last, we also looked at how we can use V equals KQ over R for a formula. Just know that the Q, oftentimes we did not look at the positive and negatives, especially in Coulomb's law, but for voltage, the positive and negatives do in fact matter, and it matters a lot. All right, we can add them all up at the end, so it's actually pretty nifty. All right, that is it for me. I'll see you next time. Bye-bye.